Andy Oertel on preprocessing and presolving. We will hear about these more powerful so-called strengthening rules and what they can be used for. So Andy, please.
Yes, thank you, Jakob. Yeah, as Jakob said, we will basically look at things that are done before we actually get to solving. So what is like the reformulation techniques that are stronger than just solving. And well, I should note that this work was not just done by me myself, and we have a lot of collaborators that make this work that I show possible. So we are looking especially at optimization problems and two optimization problems specifically. So let me introduce them to you. The first one is 0-1 integer linear programming. And here, well, I should mention that this is like specialization of mixed integer programming, which you might know. And the problem is that we are given an integer linear objective function that we want to minimize. And we are also given constraints, which are integer linear inequalities. So basically the goal is that we want to satisfy all the inequalities. We want to find like the minimum solution that satisfies the inequalities and minimum with respect to the objective. And important here is, and that's why it's called 0-1 integer linear programming, is that the variables only take Boolean values, so 0 and 1. The other problem in the title is the MaxSAT. That's also an optimization problem. And despite its name, it's a minimization problem, of course. And the idea is here again that we have this integer linear objective that we minimize. And as constraints, this time we have clauses. So the variables are again Boolean, and so they are 0, 1. And we're interested in the optimal value of this objective, subject to satisfying all the clauses. And well, when you think about this and compare this to the previous problem, then you can think about clauses as just saying that at least one of the literals is true. So we could also just say this and then see, well, this is somewhat of a 0-1 ILP. Then, well, so far in the previous tutorials, we always had this view that, well, we have the problem, and we give it to some solver, and the solver returns us some result. But this time, we are now in this talk looking closer at what the whole workflow actually looks like. And what most of the tools, most workflows look like is that you first have a preprocessor or presolver that reformulates the problem somehow by some techniques, and then hence like a nicer problem that the actual solver can work with better to like the solver, to the core solving technique. And why we have these two names, presolving and preprocessing, it's basically just coming from the two communities that that came up with these techniques, or like that came up with techniques. So in the MIP community, this reformulation is known as presolving, and in the MaxSAT or the SAT community, it's known as preprocessing, but essentially it's the same thing. So, and these preprocessing and presolving techniques, they can be either tightly integrated to a solver, and then you can actually also call like these techniques during the solving loops. And that's then this is done like in SAT solvers quite often. But it's also possible that you have them as completely independent tools. And then you have really the separated workflow where you're having a tool that gets the original problem, gives you then an output problem, like also again as a file maybe, and then you hand this file then to the solver. So this preprocessing is extremely important to get the performance. So it's a really important technique. And to show this, like we can look maybe at 0-1 integer linear programming, or MIP for here. And this is like a survey by Achterberg et al. And they looked at presolving techniques in MIP. And here, well, for all the problems, they improved, like presolving improves the solving time by over 3 times. And especially for larger problems, we are getting a huge speed up by almost 20 times. And again, also for the other problem by MaxSAT, there is this MaxSAT independent tool or standalone tool, MaxPre, which this is like plots from the latest paper, where it shows like the red line that's MaxPre, and it shows like we want to lower is better basically in these plots. So we can see that preprocessing helps to improve the performance significantly also for MaxSAT. So it's an important technique, but well, we're interested in proof logging. That's why we have this tutorial here. And so we're having this workflow, and good thing is for the solvers, well, the previous tutorials already talked about how to get certification for them. And especially for mixed integer programming, there's this Viper system which can do like basic certification for mixed integer programming. And then for MaxSAT specifically, there's Verify which can do a lot of MaxSAT algorithms. But then the issue is that, well, this only certifies us that this problem or this result is correct with respect to the reformulated problem. But how do we know actually that we solve the correct problem? That like this result is a correct result with respect to our problem. And for this, we also need to have certification of the presolving done by the presolver and preprocessor. And this is exactly what I will talk about in this tutorial. So we do a look into certification, and I'm actually also will talk briefly about how to get a formally verified checker for these proofs, reformulation proofs. And we have like a framework to like get new checkers for different paradigms. So the structure, what we will look at is that first, the next thing we will look at is how our proof system looks like and how we actually do these pre-processing proofs, like what these reformulation proofs look like. Then we will run through a complete example so that you can see like how this is actually applied in practice. Then I will briefly talk about this for verification. And at the end, we have some experimental results to see like what is actually performance, like how good is this in practice and usable. So and I should mention, if you have any questions, then just please ask and feel free to interrupt me. So to start off, let's take a step back. That's for preliminaries. So we are, as you've seen, the two problems we studied, they are Boolean variables. So we have the domain 0 and 1, which correlates to false and true. Then a literal is either the variable x itself or its negation x bar, where we say that the negation is 1 minus x. And then pseudo-Boolean constraint is just an integer linear inequality over these literals, like for example this constraint here. So basically a pseudo-Boolean constraint, it's basically just the same as a 0,1 integer linear constraint that we saw before from the 0,1 ILP. Then an equality constraint, it's just syntactic sugar for two inequalities. And the clause is, well, either a disjunction of literals, or equivalently, we can say that at least one literal is true. So it's also just at least one constraint in PB. So especially with this, we can see that the MaxSAT problem is just a special case of a 0,1 engineering program. Then what is the idea of the proof that we want to do? So what is like main invariant that we want to get out of this proof? So we're having, this is our workflow, and we're generating this proof. And for every step that we're doing in the preprocessor, we also want to have a proof that this step does not, or that this step preserves the optimal value of our problem. So each time we're doing some modification to the problem, we want to preserve that the optimal value of this problem always stays the same. And to do this, we use a separation separate our constraints in two sets, which are the core constraints, this core set of constraints you see. And on this, we have a strong guarantee that the current objective, or that the optimal value of the current objective, subject to satisfying all these core constraints, has the same optimal value as the original problem, our input problem. So the original objective function subject to the original input constraints. And the other set that we have is the derived set. And for this set, well, that's basically when we derive the constraint is first added to this set. And the guarantee that we get implicitly for this set is that any solution to the core set can be extended to a solution that satisfies the core set and the derived set. And here, like a small notice that, like, if you're familiar with like SAT, preprocessing, interprocessing, and especially the paper by Yavisalo et al., then the core set there is called irredundant clauses, and the derived set is called redundant clauses. So that's just a side note if you know like the SAT, interprocessing, preprocessing. And then, well, we can move constraints from the derived set to the core set. So the idea of the proof is now that, like, yeah, each step of the reformulation is represented by some proof rules in our proof system, and then each proof rule preserves the optimal value. So by each proof rule step, we keep the invariant that the optimal value is the same. So basically, then for each, like, when we go through this proof, then step by step, then especially also at the end, we have the same optimal value of so at the end of the proof, for the problem, our current objective and our current core constraints have the same optimal value. Like, this problem has the same optimal value as our input. So what we basically can now check is that the core constraints and the objective at the end of our proof match up with the output problem returned by our preprocessor. So this reformulating problem here. And yeah, this then basically by transitivity, this gives us a guarantee that the input problem has the same optimal value as our reformulated problem, or that's outputted by the presolver. And this checking that the core constraint and the objective matches up with the output problem, this is basically just a syntactic check, where we check that for each constraint in the core set, there's a constraint with that's syntactically equivalent in the output problem. So, and then what are these proof rules that we're looking at that have to preserve this invariant that the optimal value does not change? So first, we have this cutting planes proof system that, yeah, the previous talks also talked about. So first, so here are some basic set of rules of the cutting planes proof system that's like sufficient for like get a complete and sound system. So we have first here literal axioms. So you can just basically say that variables are between 0 and 1. Then we can add two constraints together. We can multiply a constraint by an integer, and we can also divide a constraint by an integer. And here we can see that because the left-hand side is all integers, like the variable is all integer, the coefficients all integer. So the sum is integer, so we can just round up the right-hand side to the next biggest integer. And here's a small example of how this cutting planes proof can be applied, how this looks like. So we start with this optimization problem here on the left, and then we use this cutting planes derivation here. So we first derive the literal axiom that x2, not x2 is greater than equal 0. We multiply it by 2, and then we add it to our constraint 42 up here. And that results in this constraint here. So why is this the case? Basically, this 2 times not x2 cancels out with 2x2. This leaves a constant 2 here, which then we normalized by moving to the right-hand side. So this is then 3 minus 2. So we only have 3x1 plus 3, not x3 greater than equal 1 as the result of the addition. And then if we divide by 3, then the coefficients get divided by 3 to 1. And our right-hand side is 1/3, which is rounded up to 1. And this basically then gives us constraint 43. And in the syntax of our file format for these proofs, this is basically illustrated in represented in reverse Polish notation. So you basically have a stack to compute your things. So you're first basically deriving this literal axiom, which is just stating literal. So if you have a literal in this cutting planes derivation, then it's the literal axiom. This is pushed to the stack. Then this integer is pushed on the stack, and then we're doing a multiplication. So this pops like the last two things from the stack, and like the last thing should be like this integer, and then the previous thing is this constraint. And so it's multiplied by 2, and this literal axiom is multiplied by 2. Then we load constraint 42, and here I now use that so the equation numbering I have in my optimization problems matches up with like the constraint ID. So every constraint has an ID with which I can reference this constraint, and this matches up with the equation. And then I add up this multiplied literal axiom with my constraint 42, and finally divide by 3. So yeah, you can also just match up the colors that I have in this slide. Then the cutting planes rules, they just preserve solutions. So we say that the cutting planes rules only can derive implied constraints. So constraints, so with them I cannot add or remove solutions. But in preprocessing especially, I often want to remove solutions. I want to or add some solutions by adding like a new variable that expresses something. And to do this, we have the redundance-based strengthening rule that the other tutorials also talked about already. So we have the substitution, which maps the variables to truth values and literals, or literals. And then we basically, what we check is that we can introduce a new constraint C with respect to our current derived constraints and our current objective, if this implication holds. And what this basically says is that this witness, or the substitution here, this omega, this patches up our current solution. Like if like a solution is falsified by this new added constraint, then we can repair it with a valid solution using this using a substitution, and this has to satisfy like all the constraints and that the objective is not worse with respect to this new solution. And for this rule, we explicitly need that the substitution is given explicitly, and we should also be able to check that this implication holds. And this can either be done because it's obvious to the proof checker, or we have to give an explicit cutting planes proof that shows this implication. So how do we apply this? So for example, we have this redundance-based strengthening application here, where we want to derive that not x3 is greater than or equal 1. And the witness that we use is x3 maps to 0. And well, why does it hold? And that's basically, this is simple enough that the proof checker can figure this out by itself. So we have to go through like everything that we want to check that is implied. So first we look at like our current derived constraints, and our current derived constraints are at the moment just this constraint 42. And for this constraint 42, if we plug in this substitution that maps x3 to true, so this becomes and the x3 to false, so not x3 becomes true. So this is just a constant 3, move to the right hand side, so this becomes trivial constraint, basically x1 plus 2x2 greater equals 0 is just always true. You can always, like any solution satisfies this. Then the constraint, then we have to check that the constraint that we want to introduce under the witness, under substitution is also trivial. And well, plugging in the substitution, we get that 0 is greater equals 0. And then for the objective condition on the right hand side here, we get that the substitution x3 is not in the objective function, so the left-hand side and the right-hand side of this inequality is the same, so this also holds true. Then what are strengthening rules used for, or what is this? Basically, for basic symmetry breaking, we can use it. We can also use it for some loss of generality reasoning, and we can introduce extension variables. We will later see the example, like an application. And then there's also an additional strengthening rule, which is called dominance-based strengthening. There's a paper on it if you want to read more, or you stick around for the next talk by Markus Anders, who will talk about symmetry breaking and proof-looking blocking for that. Then, well, so far we only looked into how to add constraints, how we add more and more constraints, but in pre-solving we want to simplify the problem, so we also have to delete constraints. But we have to really be careful when deleting constraints, because, well, arbitrary deletions are unsound. I can, well, if I delete all the constraints, I can have an optimal solution, or I can have better than optimal solutions. And actually, with this dominance-based strengthening rule, it's even possible to show worse, or to show that worse than optimal solutions are optimal by this proof. I can basically remove all the solutions. So we really have to be careful when we do deletions. And the way what comes into play here is these two sets. Like here, these two sets, these derived and core constraints come into play. And it's basically because for this derived constraints, because we have this implicit guarantee, we can, that any solution to the core set extends to a solution of the core and derived set. Any constraint in the derived set can just be deleted, because we, well, just because we just have a guarantee on this core set, and, well, this derived set could be more strict, but it's not giving us more solutions to this core set problem. Then the only restriction that we have is then if we want to delete something from the core set. And there we basically have to show that we can rederive the constraint we delete by redundance-based strengthening. So then it's basically showing that that the constraint, or the constraint we delete is not a constraint that is that, like, without it we would allow solutions that are better than optimal. And this can basically be done by redundance-based strengthening, only in the, like, opposite direction. And for this we only can use core constraints, but without the constraint we are deleting. So we basically have this implication condition out here, and this is like, yeah, basically this is by redundant-based strengthening, except that for the core and derived sets we can only use the core set without the constraint that we are deleting. But then we also only have to show that our constraint that the constraints from the core set without the one we are deleting under the witness is applied. So how this works as an example is, for example, when we have this constraint 42 now here, and we want to delete it, then we can do this without a substitution. So it's basically implied. Like, without a substitution would mean it's basically like redundance-based strengthening, where in redundance-based strengthening, when we have a substitution, this means that we're doing some reasoning that's like implied. We're having the same set of that we have not the same set of solutions, but if we just have an empty substitution, then we are just deriving something or deleting something without changing the set of solutions. And then checking that this deletion works is basically can just be done by propagation. Like, we can see when we go through our conditions that have to hold, then first when we look at the core sets without the deleted constraint, this already exists on the right hand side, because, like, we have no witness now, no substitution. the substitution is empty, so this is exactly syntactically the same. And for the objective condition, we also have that, like the left-hand side, the right-hand side of the inequality are the same. It's only that the deleted constraints, there we have a condition, and we basically have to show that we can derive this constraint. But this constraint that we're deleting, like this constraint 42 here, it's definitely always true, because x3 is always 0 by this constraint. So that x3 is always 0. And x3 being 0 means that this not x3 is 1. So we have a constant 3 here, and this constraint 42 is always satisfied. And we can also actually show this with an explicit subproof. So this is then, so either, like as I said before, either this like implication that we have here, it's obvious to the checker, which it is in this case, but we can also make it explicit by adding a cutting planes subproof that derives this. And here we're basically using proof by contradiction. So we are introducing this negated constraint, of the negation of the constraint that we want to delete, which is expressed in this implication as this part here. And then when we add the constraint that propagates x3 to false, so this constraint 43, such that it cancels out this term, the x3 term in constraint 42. Then we get that, like we have the negation, we add 3 times this constraint 43. Then we get a constraint not x1 plus 2 not x2 greater equal 4. And because our variables or our literals are only domain 0 and 1, this is a contradiction, and this can never be satisfied. So this is a contradiction, and then we use this -1 int here, which refers to the previous constraint. So we're saying here that the previous constraint is a contradiction, and this ends our proof by contradiction. So for
the date pick here, and it just 43 was a previously derived constraint. You silently moved it to core.
Yes, exactly. So it's actually the problems are a bit different to what the previous problem looked like.
Okay.
So it's not the same problem. It's not the one example that I'm carrying along here. The one example I'm carrying along comes in the next section of the talk. So yes, so this constraint 43 is in the core. It's like both of them are in the core. It's important. So now we can add, remove constraints, but what will we do about the objective? And here we have the objective update rule. And this rule just lets us change the objective from an old objective to a new objective. And yeah, a lot of reformulation techniques do this. They change the objective. And the way we can do this is, so what we need to check to change the objective is that we have an equality showing that the old objective is equal to the new objective. And this can either be done because it's trivial, like the checker can obviously see that it holds, or by an explicit cutting plane proof. And an important note here is that for showing that this equality holds, we can only use constraints from the core. Because there is this one direction that the old constraint is less equal than the new constraint. And if we would derive this using derived constraints, then we could introduce better than optimal solutions. So there's like a sample example that you basically your new objective just consists of new variables, fresh variables that you introduced, so that they have nothing to do with like the old problem. But you have introduced enough variables that you can show equality between the old objective and the new objective, which is just fresh variables. And these definitions, they live in the derived set. So if you would have this derived set, if you could derive this by the derived set, this equality, then you could show this objective change. And now you're deleting, like you're free to delete any derived constraint. So deleting all these relations between the original variables that your problem is over and these new variables. And then your objective is completely free and you can claim whatever solution you want. So we need a restriction that we can only use for constraints. And then the question is how to specify this new objective, and there are two ways. So one way is that we just state the new objective that we want to derive, and this is good if we have large objective changes and the new objective is rather small, because then we just have to write this new objective, the small new objective. But usually you have small objective changes. You're just adding like one term and removing another term. And for this, we have this other way to specify this specification by difference between the new objective and the old objective. And this is then good if you have a small objective change. I will show briefly in a few slides how the syntax for this works. But let's first see why we actually need this objective update rule. So why do we even need to bother about this changing objectives? And the reason is that the redundance-based strengthening steps, and especially the witnessing, or like these substitutions, they become extremely complicated and up to impossible. So, for example, let me consider this optimization problem here. And if we look closely, like this is greater equal, less equal, we could move x3 and x4 to the right-hand side and get an equality between these, like between x1 and x2 is equal to x3 plus x4. So we could use this to update our objective to x3 plus x4. Now, if we want to do a deletion of one of these original constraints, so originally we had this constraint here, and we want to delete this now with the substitution that maps x1 to true, then, well, if our objective is unchanged, like here, then we have this objective condition, this objective improving or like non-worsening condition. And this gives us that, well, x1 plus x2, so this is our objective, is greater equal than 1. So this is the substitution of x1 to 1 plus x2. So we basically have to show here that x1 is greater equal than 1. And this is not trivial or not directly obvious how to do this. However, if we change the objective, just as the preprocessor presolver did, then, well, our substitution does not change the objective. Like there is no x1 in the new objective. So this objective non-worsening condition is trivial, and this makes our life so much easier. So we actually need this objective update rule. Then for an example, how this objective update rule looks like. So we have, let's consider this problem here. And we can see that where the first constraint basically says that 3 not x2 is greater equal to x3 plus 1. And the second constraint says this is less equal. So these are the two conditions we need for the objective update. So like we have for the objective update, so we can change our objective that contains 3 not x2 and replace it by 2x3 plus 1. And we can even do this by just directly saying what our new objective is. We're just specifying that our new objective is 2x1 plus 2x3 plus 1, this constant 1. Or we specify the difference. And here for the difference, what we basically say is that the terms that we introduce new to the objective, they appear positively. So we're adding to the objective 2x3 plus 1. And the terms that we remove from the objective, they appear negatively. So minus 3 not x2. And then we can compute the new objective just by adding this difference to the old objective. Yes, Adrian?
Yeah, I don't quite understand your example in the previous slide where you said like, oh, okay, this is very hard to do. So You have the equality x1 plus x2.
Yes.
Why can't you just use it to, to basically rewrite it?
Yes, that's exactly the thing. Like, you could do this.
Yeah.
It's not like impossible for this problem.
Yeah.
The only problem is that you're doing like these rewrites multiple times over and over, and like you're changing your constraints in between, and then you're doing more rewrites and so on. And what you would need for, like, without changing the objective, for your idea, what you would need is to always carry around these equalities, like still have them in your problem. Like, then it would work, but we would like to avoid this and have the problem as small as possible. And then also, like, well, it reflects what the presolver is doing, so it fits nicer to like the algorithms that we want to certify, or that we want to have certification for. Yes, so then let's look at an example. For example, so when we have a proof, then we first start with a header of the proof, and this specifies just the version that we're using of the proof format. And then what we do next, what is done in the proof then, is that all the constraints are loaded from like a problem file. In this case, we use the OPP format. So this on the left-hand side here is an OPP file, or OPP format the problem, which corresponds to the problem on the right-hand side. And here we're also assigning constraint IDs to like the constraints. So the first constraint gets ID 1, second constraint ID 2. Then let's get to our first technique that we are applying. And here, well, we can see that the first two constraints, they basically say that this constraint, this variable x1, is equal to not x2 plus x3 plus x4. So we can substitute this variable x1 out of this constraint 3 by basically using this equality here. And to do this, or how to certify this, is that we take the right direction of this equality and add it to the constraint 3. And what I mean with right direction is, well, we want to cancel out this x1 here, or this not x1 here. And to cancel this out, we need the constraint that contains the x1 positively, and this is constraint 1. And they have the same coefficient, so we just add them together, and from this, it results, we get as a result constraint number 4. Then, well, we do the substitution, but still we have this constraint 3 around. So now we want to delete this constraint 3. And to do this, we do a deletion with a subproof. Here we actually need this explicit subproof. And so we're doing a proof by contradiction, which, well, we add the negation of the constraint that we delete, which is x1. So the negation is x1 plus not x5 greater equal 2. Then basically we recover the negation of the constraint we just derived by adding the other direction now. Like we've used this constraint 1 of the equality to derive this new constraint. But now to show the deletion, we need the other side of the equality, so this constraint 2. And this, adding this constraint 2 to the negation, gives us the negation of the constraint we just derived, this constraint 4. So if we add the constraint 4 now to this negation of the constraint 4, basically, then we get a contradiction. Because the constraint like the negation of a constraint and a constraint are not true at the same time, so this obviously gives us a contradiction. And then we end this subproof by saying that this constraint, the contradiction, that we have derived the contradiction in previous constraint.
I'm going to nag you again, but just am I correct now that we would actually need a move to 4 command in between?
Yes.
Now we seem to be using 4 in the deletion.
Yes, no, exactly, that's true. Like we need to have constraint 4 now in the core. So this, yeah, here in between we would have a move to core. That's a good point. So then, yes, so we have done this substitution here. Now we can also use this equality by just like changing it slightly and having that x1 plus x2 is equal to x4 plus x4, x3 plus x4 plus 1 to change our objective. So basically constraints 1 is saying that the old objective is greater equal than the new objective, and constraint 2 is saying that the old objective is less equal than the new objective. So these are exactly conditions for the objective update. And so we can basically just change the objective by saying that our new objective is now x3 plus x4 plus the constant 1. And what it actually gives us now, or what we can see now directly looking at our problem, is that the objective or the optimal value for this optimization problem is at least 1, because we have a constant 1 now in our objective. So now we did enough manipulations with this equality constraint, did all the substitution, we did the objective update. Now maybe we can actually get rid of it. And we can actually get rid of it because the
sorry, Andy,
yes.
I'm getting tired, but can you explain why very PB just realizes this?
Yeah, because it basically just sees that, well, x1, the constraint 1 and constraint 2, they are both in the core. So we've started out with them. And they are syntactically equivalent to basically saying that old objective is greater equal new objective. This is constraint 1. And constraint 2 says that the old objective is less equal than a new objective.
Oh, so what you're saying, very people will say, oh, you want to change this objective to this, then I want you to derive the 2 following constraints for me, but then it will check and will say, oh, I see now that the first constraint I want is in fact constraint number 1. Yes. The second constraint I want is in fact also already in the database is constraint number 2. I guess I don't need the proof then, sorry.
Exactly, it exactly says, okay, I want this and this constraint, and it sees, oh wait, this is syntactically equivalent to this one, and the second one is syntactically equivalent to this one.
Okay, thank you.
So now we want to delete this equality. And well, for the one direction, like deleting the first constraint, we still have like conditions here that like our variables x2 and not x3 and not x4 have to be like at least 2. And like if we just would remove this x1, like we still have conditions on this on these our variables except an x1, but then we see that we have this constraint 4, which gives us the same guarantees. So this lower bound, like plugging in, so plugging in, so plugging in one direction of this, the one direction of this equality, it's like not trivial to show, like this direction from the first constraint. Yeah, the gradient direction it is. And so here we now delete this constraint 1 by redundance-based strengthening. So we get the negation of constraint 1 as like an additional constraint that we have available to prove things. And then for the deleted constraint under the substitution, we get that we still have to show that x2 plus not x3 plus not x4 greater equal to 2 is implied. So we still have to show that this lower bound on like these literals hold, or then lower bound on the literals hold, like that at least 2 of them are true. And this is actually given by this constraint 4. So we can basically weaken away this x5 here. So if we weaken this away, like adding a literal axiom not x5, then this cancels out to a constant 1. So the right-hand side reduces to 2, and this is exactly the constraint that we need to show that it's applied. And then again, for like the second constraint, we need also show that the second constraint under the substitution is also applied. And this is done, well, by adding it up with the negated constraint. Or by looking at the negated constraint here again, if we add the grade x1 greater equal 0 to this negated constraint, then this cancels constant 1. So this literal is greater equal 1, which is exactly this constraint 2 under the substitution. And then finally, for the fourth constraints, well, the substitution does not change anything. So then we have on the, we already have it in the database as a core constraint. And we have it as an implication. So that's trivially implied, it's syntactically the same. And also for the objective, we the substitution does not have any effect on the objective. So on the left-hand side and the right-hand side, for this objective condition, we have the same term. So this is also trivial. Good. And then for leading the other direction now of this equality, so leading constraint 2, that's a bit simpler because here this here we have only that if we plug the substitution into the constraint that we delete, then this constraint becomes trivial, so we don't have to show any bound on this literals. So here we just have a greater equal 0 with this witness, with the substitution. And finally, also for this constraint 4, and for the objective condition, here again, x1 does not appear in this constraint or the objective. So there again, trivial, as they do not change the objective or the constraint 4. So and finally, we can do some so-called duality-based fixing, which is basically just fixing variables to a value without loss of generality. So we can say that x5 and x2 and x5 can be fixed to 1, basically because, well, they in all constraints they only appear positively as literals and with a non-negative coefficient, and in the objective the coefficients are 0. So they only help to, like setting them to 1, x2 and x5 only helps to satisfy this constraint more. And x3 and x4 can be set to 0, as basically setting them to 0 only helps to satisfy this constraint more and reduces the objective. And so to do this, well, do this effect basically on the plugging in this fixing into the constraint, which then trivializes and is completely removed. So we can just delete this one constraint, the one remaining constraint, constraint 4, by using this substitution, mapping x2 to 1, x3 to 0, x4 to 0, and x5 to 1. And this, as I just said, is basically plugging this substitution into the constraint, results in a trivial constraint that basically just says that 0 is greater than equal 1, which is always true. And the same is also for the objective, that x3 plus x4 is greater than equal -1, which is also always true.
Could you also do this using redundance?
Like you could basically for removing this x3 and x4, you could add constraints saying that not x3 is greater than equal 1, and not x4 is greater than equal 1 by redundance. And then, but then you still have like these constraints around that say that not x3 is greater than equals 1. And then you also have to delete them at the end. And this is just doing it in one step instead of like these multiple steps with what you proposed. Yes. And so basically what we now can see that we've reduced our problem quite substantially now, and now it's very obvious to see what the optimal value is. So what is it? Has someone idea? It's actually 1. So we can just like want to minimize, so setting them x3 and x4 to 0, and we can just set x3 and x4 to as a value we want. So 0 would be the, so we have the optimal value 1 by setting x3 and x4 to 0. Good. And then to wrap up the proof, we claim that the output problem, or like the problem that we have at the end, is equi-optimal, so it has the same optimal value as the original problem. This is this equi-optimal claim. And then this file here only means that, well, this reformulated problem where we want to check against is given in an additional file. So we have an additional file of a problem that's outputted by the preprocessor. So this preprocessor is an independent tool. It takes this input problem and returns the output problem. And here we have and writes this output problem to a file. And here we're given this reformulated problem as inside a file, and we check that this problem in this file is equivalent to the constraints that we have at the end, problem that we have at the end of the proof. Then we have no conclusion. We just have done reformulations, and we end the proof.
If you want to do an end-to-end verification of your solver, then you would do one logging for the preprocessing, and then another file for the actual solving.
Yes, you could do this. Like you could do like 2 files or copy these things together, but you can actually also, what we propose here, have 2 files, one file for the preprocessing and then another file for the actual solving, which can be independently checked. Yes.
But then you have to have a machinery around that's working with both files.
Exactly. Exactly. That's the.
But having it in one large file.
Yeah, but we want to avoid this because what the idea is that, well, you have this preprocessing tool, and maybe you're doing some expensive techniques for preprocessing. So you maybe only want to do this preprocessing once, and then hand this preprocessed formula to different solvers. And so you're solving, and then like you do like a portfolio or so, and then like one solver returns, yes, I found the answer, and then you basically have like a separate proof for this complicated preprocessing that you did, and then this proof of the solver that found the result. And then you can like easily just connect them with this idea of having simple proofs. Yeah, Florian.
In practice, how are these objective reformulations handled in the end? Because usually if I want to use a MaxSAT solver, I want to know a solution to my problem. And it seems to me that like in the end I will get a solution to like maybe a slightly different, smaller problem.
Yes. Yeah, you will have also different variables and
yes, so how is this handled?
Yeah, so there is basically by going backwards through the proof, you could reconstruct like a solution to the original problem. And like all these preprocessing tools as a shorthand, basically, they also return you a mapping from like the original, like this reconstruction stack, basically. That is, for example, it's known in the subsolver world. They also have like a reconstruction from like this reformulated solution in this reformulated problem to a solution of the original problem. And the tools, they do this, or you could do this by going backwards to the proof, but it's not supported yet by very. Yes. So yeah, then this is like the whole example that we just went through. And as Jakob pointed out, it's actually true. Yeah, here should be move to core. That I will add this when we put the slides online. So now we have this proof. We check it. We have our verifiability, which is not verified. So why should we actually trust this verifier, this verifiability that the proof is correct?
Andy would never write fuggy code.
Florian knows that. Right, doing his fussing, or like doing fussing on Matthias. So, so of course, why should we trust the result the proof is correct, that the checker returns to us. And the idea, of course, would be to have like a formally verified checker here. But the issue is that then we have a very restricted proof format here, which we want to avoid. Like we want to have it as easy as possible for solver authors to write, to integrate proof logging into their solvers. So we have, so the idea is basically that, well, the solver authors can write the normal proof that's a do for VeriPB, but then VeriPB act as an elaborator, which basically takes this syntactic sugar in this, which is easy for proof logging, and elaborates it to a very simple format in an elaborated proof. And in this elaborated proof, this is simple enough that we can actually do a formally verified checker. And then this formally verified checker, it is like correct and gives us this, gives us a verified result. And instead of trusting me, what you now have to trust is the following. So you have to trust that, the higher order logic definitions of the problem that you want to solve and the parsers, that they are correct, but they are kept simple as possible and should be easy to check. Then, well, you have to trust that like the people that designed CakeML and that they got the model of the system that you're running the code on, that they got it correct. But this has been validated extensively in papers and by certification, also by validation. And then, of course, what you also have to trust is the whole for theory improver and like its implementation, its logic. But here, well, it's this theory improver. It has like a separated and trusted kernel, so every inference goes through this kernel, and so you can make sure that the proofs are actually correct, or like the software, the KPB, that of our formally verified checker is correct. And that's when it says, yes, I accept this proof, then actually this proof shows the real correct result.
But one interesting point here, right, is if you don't remember the cutting place rules, so this looked a little bit mysterious, you don't have to trust that this proof system is correct. Like pseudo-Boolean proof logging, you don't have to trust that at all.
Yes.
Which is kind of interesting.
And so the way you're thinking about like this must be complicated, designing a new proof checker, and so, or like adapting it to your problem that you want to solve. And we made it as easy as possible and as extensible as possible, or to implement or to have this approach that we have here for checking through reformulation proofs. So our checker, formally verified proof checker, is basically set up in two components, where we have a front end and a back end, and then up here we see our proof getting in. Like we have the reformulation proof, then we have the elaborator, and this is the elaborated proof. And what the formally verified checker does, it first encodes like from the original problem, here for example MaxSAT, this MaxSAT problem into PB, and it also encodes like the output problem, like the one returned by the preprocessor into PB. And then all the reasoning and all the complicated stuff is done in pseudo-Boolean reasoning, so by this back end. And then at the end, we check that the problem at the end of the proof is equivalent to the output problem, and we return yes, it has the same optimal value or not, right? We give out an error. So basically, if you want to change to a different problem domain, maybe you want to do 0-1 engineering programming, or you're Kieran and you want to do craft problems, then the only thing you have to change is basically this front end that encodes the problem that you have into PB. And Yong-Kian will talk more about this tomorrow when he talks about KPB. So now we've seen how this tool works, so maybe let's see how this performs experimentally, how well. And so for 0-1 engineering programming, presolving, we implemented pseudo-Boolean proof logging into the presolver Papilo. And we've covered like all the techniques that are used by that are applied to 0-1 integer programming by Papilo, and the proofs are checked with VeriPP. So at this point, so for this experiments, the proofs were not checked by this formally verified pipeline. It was just VeriPP that checked the proofs. And for the instances, we used PP competition and MIPLIP, instances as benchmarks. So then first, let us look at what extra time is required for writing the proof. And well, here this relative time means like how much, or like how, like basically one means it is the same time as without proof logging. So we have very low overheads for writing the proof, up to like just 6% here for this one problem class. So writing is very efficient, but then when we look at checking the proofs, then we see that we have quite large slowdowns. And well, the good thing is we managed to check all the instances that we could generate proofs for. But yeah, this slowdown is like that VeriPP is up to like almost more than 20 times slower than Papilo, than the presolver Papilo. And there are several reasons for that. Well, Papilo works parallel, VeriPP is only sequential. Then the experiments were done with the old version of VeriPP and the new version that we have coming up, but that does not support presolving and preprocessing yet. Should be faster, and it's also for reasons that Wietse talked about, that like the Papilo has like a lot of data structures, specialized data structures for this presolving, which makes it fast, and then VeriPP doesn't have these data structures and really has to check every inference separately. Yeah, Florian.
Are these like typical runtimes for Papilo? So will it always finish within a second, or otherwise you won't preprocess the formula?
No, that's typical runtimes. Yes.
In that case, like waiting 20 seconds for your result is not that bad compared to probably the rest of the solving.
No, exactly. Like this is actually like full, like applying to the end all pre-solving techniques that it could do. And so Papilo is really fast in that sense. And yeah, just having pre-solving then done in 10 seconds instead of 1 second, it's still quite good. Or like checking that the result, that the pre-solving is correct in 10 seconds. Or pre-solving that you've done. That's still very short time. Good. So then also for MaxSAT, we implement this in the standalone MaxSAT preprocessor MaxPre. We covered all the techniques, and here we also use this formally verified checker CakePB to formally verified results that our proofs are correct. And here we use the MaxSAT evaluation 2023 instances to evaluate. And here we can see that for writing the proof, we are way worse than for 0-1 integer programming for its presolver Papilo. Like 64% slower in the mean. And the main reason for this is that the MaxSAT file format expects that all the variables are numbered sequentially. So basically at the end of this reformulation proof, we have to rename all the variables to basically compress them sequentially. So have sequential numbers. And we currently do this using redundance-based strengthening, basically saying, oh, this new variable name is equivalent to this old variable name, and then throwing away the old variable, and then basically substituting with this equality. So it's a lot of overhead, and it might be an idea to actually introduce a new rule for this renaming, which we might do in the future. And then for checking, we have huge slowdowns. So the pipeline of VeriPP requests. So this is VeriPP plus CakePB. So checking, elaborating plus checking with the formally verified checker. And so we have slowdowns of like, around 100 times. And most of the time is actually spent in VeriPP. So VeriPP is like really the bottleneck here for checking the proofs. So we hope really that with the new version of VeryQB, these performance numbers should improve and we should get closer to the KQB performance. And also KQB has improved since we did these experiments. So to conclude, what are the takeaways? So I showed you in this tutorial how to do proof logging for reformulating optimization problems. And this is as best possible in the VeryQB proof system. So we just have to justify all the techniques using the proof rules. Then these proof rules, they preserve the optimal value. And the only thing that we have to take care about is the repeating constraint, and that we also need a rule for updating the objectives. We make it possible that by this output footer of the proof, make it possible to have standalone proof logging for reformulation tools, so that you can check that the problem returned by the presolver or preprocessor has the same optimal value as the input problem, and you provide formally verified verification framework for these reformulation problems, where you just have to change the front end. The next challenges would be to have the proof logging for Lund presolving, so supporting integer variables and rational coefficients, which there's preliminary work on already about the theory, how this could be done. And then another thing would be to generalize reformulation proofs instead of just having, like I showed it here for optimization problems, but could we do it also for enumeration problem, counting problems, so that we preserve the count of solutions and like the solutions that we have in the problem. So with that, thank you very much, and that's also.
Questions for Andy?
Slide 29. Philosophical question about lies that we tell people when we're explaining proof logging.
Yes.
The lie from the result to the error from result to verified checker. Should that be there?
In this case, yes. Like in this problem that we do, yes, because like the result is the file that the preprocessing tool outputs. So for preprocessing and presolving, this is actually the case. Okay. But yeah, we have, like for example, Tobias Paxian and Armin Bier, they have like done parsing of MaxSAT solvers, and there it's like the case that the MaxSAT solver claims or outputs like an optimal solution that it found, but then this doesn't correlate to like the optimal solution proven by the proof. So we still have to trust, we don't check that like the output by the solver matches what the proof claims.
Yes, I'm increasingly thinking that actually the result should be coming out of the verified checker. Only out of the verified checker.
Yes, or like out of the proof that the verified checker checked.
Yeah.
Matthew.
This is sort of a related question, but if you're just looking to get to the verified result as fast as possible, would there be any question of whether the unverified checker should be bothering to check at all, or whether it should just be elaborating? Would that save that much in the end?
There, like for rough checks, which is like the most parts of like elaboration, that would not save a lot. In some cases, yes, like if you have a lot of like things already elaborated, like if you have a lot of these cutting plane steps, these poll lines, then these can just be skipped basically, or like we just have to like, well, we still need to compute them, like
yeah,
that's the issue, like not a lot that you can say really with just elaborating, but because like currently we're checking and elaborating at the same time. Florian.
Right now, the tool and the proof format of proof checking system are called the same, right? VeryQB.
Yes.
Will this change once you're finished with your new shiny tool? Will it get a different name, or will it inherit this?
It will also be VeryQB, so.
So this version of very PB right now will just die and be replaced.
We probably live like on a separate branch or like on an archived repository or something. Then rename like very old, then we have very PB, which is like.
Because I thought like PB oxide was a nice name, but and it avoids confusion between like having to say, okay, now I mean the tool and now I mean the format.
We will rethink it then maybe. Thanks for the input.
In one of your examples, you showed that you let some rewrite something because the constraints were in the database, but then you said, okay, the proof we can do this automatically. This was on slide 23. My main question is, yeah, this one. Yeah. So here, in when you implemented the proof logging, do you have many like of these unhinted lines where you skip the proof? And then are these source for the big overheads that you're seeing?
Partially, yes. That's exactly the thing that also for the we have also reversing the propagation steps. These are also completely unhindered. Then we have implemented some hints for redundant space strengthening, but a lot of things are without hints, and then the checker has to invest more time to figure out the why this application of the rule holds. And that's especially also true, especially for the experiments with the per kilo presolver, where we have very low time for logging. Here, that's basically because we don't spend a lot of time on writing this.
So we're a little bit behind schedule, but I suggest we thank Andy again.